Okay. All right. Hello. So what we're going to do today is walk through the lenses, mirrors, and telescopes lab for data collection, including observations. And what this involves is taking two different lenses of different presumed focal lengths, which we can judge based on shape. One will be more curved, one will be flatter than the other. We're going to make real images with them of this light bulb on this index card. We're going to measure the distance from the object to the lens, our object distance. We're going to measure the distance from the image to the lens, the image distance. We'll use those to calculate the focal length for that lens, which we have an equation for that we developed from geometry that is written in the lab. We're also going to take a look at the appearance of the image on the card and compare its orientation and size to the object. So, when I mean orientation, if this is our original object, it might look just the same, but possibly a different size when we look at the image. If up on the image and up on the object are the same, if left on the image and left on the object are the same, we say that it is erect or upright. However, it may be that when we look at the object and compare the image to it, the image might be upside down and reversed left to right. In those cases, we would say that the image is inverted. So we're going to make a note in our descriptions about whether it's inverted or erect, or you could say upright. And we're going to make a note about whether the image appears to be larger or smaller than the object. And to give us some judgment on that, I'm going to hold a ruler next to each at the beginning. And we can make a note of that. So first, let's go ahead and take a closer look at our object while we have our lights on. So I'm going to bring the camera a little closer just so that we can see the light bulb up close and what it looks like. And let's put a little bit of background here. So you could see approximately what the image of this looks like. It has the round bulb. It has a filament that sticks up, goes across, and back down again. When we see the image of it, there's this white bottom to the base, which might be brighter than the glass parts. And it's possible also that everything at the same distance as the light may also make an image on the card. It's just that it may not be bright enough. But if we hold our hand up near it, we may be able to get an image of our hand as well. It's not a real image over at the card unless it's actually in focus. So let's measure how tall this light bulb is, just to get a sense of that. And from the base of the bulb to the top, it's about 1.5 centimeters. So I'll mark that down. On a data table over here. Now, I'm going to go ahead and back up the, actually I'm going to move the, okay, I'll do this way. I'm going to back up the camera so that we can see the whole thing. I'm going to turn off the lights so that it's easier to see our image. Okay, so let's take a look here. We're going to go ahead and turn this on. This light bulb is about a 6-volt light bulb, and I have it hooked up to 4D cell batteries, which, if they were all perfectly charged, would be about 6 volts. And we don't want to go beyond that, or we could blow out the bulb. Now, I know from reading the instructions that we're going to find a real image on the card, and then we're also going to move the lens around and find another image at the same spot. I'm starting with the card way back here, but I might move it closer in depending on how things work out. So right now what I'm doing is I'm pulling the lens back a little bit. I see a little bit of something on the card way down low. So I'm going to go ahead and raise the light bulb up a little bit so it's lined up a little more with the lens at around the same height. Let's see. Maybe a little bit. Let's see. I'm going to actually raise the lens up a little bit. Okay, so you get the idea of what this looks like over here. And I'm going to be moving the lens back and forth. So I'm going to give you a closer view of the image here. Okay, so this does not look like a focused image of a light bulb right now. So this is not our real image. But if I bring that all the way over here, right about here maybe, this looks like it's maybe a little harder to tell over the camera, but things look nice and sharp here. Where it looks really bright and blurry down here, which is the light from the filament, it's actually a lot sharper in the real life. And up here, we can see the light from the screw part of the bulb. So what orientation is this relative to the original object? This is our first position. And if we look at the height of this, the size of this, I can take a look here, and it looks to be about 6.5 centimeters. So you can say whether it's larger or smaller. when you describe the image. Now I'm going to move around to the other side and make measurements about positions. And let me go ahead and pull back here. So right now, the optic bench here, where I've put the light and the lens and the screen, is all on a meter stick. And so I can take a look at this and make some measurements about what the object distance is and the image distance is. And let's see, this light is at about six point it's about 6.8.5 there, and it's about 8.3.5 here, 18.3.5 there. So that's 11.5 centimeters for the object distance. So that's what I go ahead and write for the object distance. And for the image distance, let's see, that was, again, I was saying 18.35 at the beginning over here. And then where that image was is at about 90.85. So that's 72.5 for the image distance. For the first position. But now I'm supposed to keep the screen in the same spot and move the lens to a different place. And see if I can get an image again. So let's take a close look at that screen again. And I shook the lens around here, so I'm going to need to adjust that again so that we can get a good view. So let's see. All right, so here is our first image. And now let's move the lens again. I'm sliding it around, and it's not in focus. And it's still not in focus. And I'm moving it quite a ways now, even so you can even see it on camera. And now I start to see a light there, but it's not a focused image yet. And now, when I get down here, we have to look really closely. I'm going to try bringing the whole apparatus close to see if you can see. Oh, while not turning off the light. So maybe it's a little hard to see here. But when we look at this one, it is definitely smaller than the previous image, and it's also smaller than the light bulb, but it is still upside down. So let's measure those. All right, so again, we were at like the object position itself was at 6.85 centimeters. Now the lens position is at 83.9 centimeters. So the object distance then is about 75.4 centimeters. No, I'm sorry. Um, 77 0.05 centimeters for the object distance, and the image distance then is 90.85 minus 83.9 yields about 6 point oh no, it's not 90 at all. No, I'm sorry. It was 96.85. What was going on there? Okay. So I need to add 6 to each of my earlier, or to my earlier image distance. So I'm sorry, so it was 78.5 for the earlier image distance. But then this object distance is 96.85 minus 83 is about 13. It's actually 12.95 centimeters for the image distance. And so we take a look at those numbers, and I ask you to see whether there's a pattern going from the first position to the second position. Remember that for this position also, you need to describe whether the image is erect or inverted. And I said it was upside down, and whether it's the same size as before, enlarged, or smaller than the original object. So now what we're going to do is try the same thing again, but with a lens that's a different shape. I want to make sure that I'm getting one that is definitely a different shape than this one. And so Let me try this one. Let me see if I made a mistake here. If this one's about the same as before. Okay, let me find another one. Okay, let me try this one. This one feels a little flatter, and I'm holding it at around the same position as the earlier one was for its second image, and I'm not seeing anything. So I'm kind of backing it up by hand. And around here, I see a similar image to before. It's upside down and inverted. And it's smaller, just like before. But we're a different distance between the two positions. Oh gosh. I made a mistake again in my measurements. It's not 96, it's 95. I'm going to fix all of these things. This is the thing about careless errors. Sometimes you notice them during the lab itself. And in doing so, you can make your corrections. Okay, so corrected image distances. Now it's 77.5 and 11.95 for the first lens, for lens 1. These are our right numbers. I kept writing down the wrong position for the screen. So let's see where that lens is now. And we're looking at lens 2. And we're looking at its object distance and image distance. So the lens itself is at 67.9 even. So that makes the object distance 61.05 and the image distance 25. No. 27.95 for the image distance for our first position of lens 2. And now we're going to take a look at the image again and see what happens when we move the lens further. So I'm moving it by hand here. I'm backing it up towards the light. And right about here, I see an image. Let me try to get it nice and in focus. Let's see if we can get you a little closer and a little more. Does that help at all? Okay. So if we take a look at it, does it look right side up or upside down? Is the filament above or below the screw part where the bulb fits into the socket? Does it look larger or smaller than the previous image? Larger or smaller than the light bulb? Well, it's about it's around 3 centimeters tall, so we can make a guess. We can remember from our image size earlier, about 1.5 centimeters, what that tells us about the size. Let's get those image and object distances. Okay. So now the lens is located at about, oh, it's hanging over a little bit. Let me see if I can make this up right here. Okay, it looks like it's 33.65 for the lens location. So subtracting the light bulb location from that, we get 26.8 centimeters. And then for the image distance, 95.85 minus 33.65 is going to give us 62.2 centimeters. So here's our data for our second lens for object and image distance. So there's another part of the lab. We do the math and calculate the focal lengths for each of these, and then what we're supposed to do is work with them together. And the way we're supposed to do this is set it up so that the flatter lens, the one that winds up having the longer focal length, we're supposed to set it up so that, let's see, we scooch the page, let's make this, we're supposed to move things around so that we can get an image again on our screen. And so I'm bringing the screen a little closer before I get this image, because the next thing we're supposed to do is put the other lens with the shorter focal length behind the screen, and right now this lens closest to our object we're going to call our objective lens, and this lens over here we're going to take a look at the image once we've taken the card away. And when we do that, looking through here with our eye, this can be our eyepiece. And I'm going to move this back and forth a little bit. Okay. And I'm going to see how well this shows up in the camera. Let me bring this, let me play with the camera height just a little bit. All right, I'm going to move this back over here. And I'll bring our lenses over. So let's see how well this works. Oh my gosh. Okay, this is not quite going to work. I need to fiddle with this just a little bit more. Okay. Okay, so let's see, how well is this working? Okay. So.
Please excuse the interruption. Will the following students please report to the black box for COVID testing? Tyler Kennedy, Genevieve Coach, Benjamin Critzer, Eleanor Cubic, Rachel Lee, Ellen Lilly, Chloe McMillan, Nicholas Vantacouris, Cameron McCrecken, Allison Neely, Colin North, Lily O'Neill, Kieran Percival, Cassandra Prechtel, Manya Sharma, Aaron Shea, Madeline Stacci, Faye Sullivan, and Alexa Toomey. There will be outdoor packing today. Thank you.
Okay, so when we look through the lenses here, both together, what we're going to see is a magnified image of the bulb. I'm holding my hand here at the same location, and you can now see a magnified image of my hand. I'm holding the lab, let's see, or I'm holding some of our notes, and you can see magnified image of the notes through the lens. We have made a telescope on the benchtop here, a refractor telescope. How big does this look compared to reading the text side by side? Here we get like 2 lines of text filling the top half, and then if we are looking not with the lenses at the same position, how many lines of text is this? Can we see? It looks like it takes about 4 lines of text for half of it. We can use that to judge how much magnification it looked like it had. And those are the main observations we need for this lab.